Hello and welcome to another video. Today we're going to be working on find longest special substring that occurs thrice 2, which is going to be the third problem in this week's LeetCode contest, and it's basically the same thing as the second one with just harder constraints. And I didn't want to do the easy one because that one's a little bit too easy, so let's just start with this one. So you're given string S that consists of lowercase English characters. A string is called special if it is made up of only a single character. For example, ABC is not special, where D, D, Z, 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 and so on are special. Return the length of the longest special substring of S, which occurs at least thrice, or -1 if no special substring occurs. Substring is a continuous non-empty sequence of characters within a string. So for example here, a substring of length 2 occurs 3 times because, and they can overlap, right? So the first 2 A's is 1, the second 2 A's is this, and this is the third one. So they kind of show you this in the picture. So that's the longest one. In the second one, there's nothing that occurs 3 times, not even a single character. And in the third one, A occurs 3 times. That's the smallest. So I'm going to kind of explain what I originally did. And like I said, it got time limited exceeded a few times. So I tried to make an optimization for it. And then once I made the optimization for it, I realized I didn't really need that at all. And then my optimization basically became the solution. So what I originally did was kind of straightforward. So let's just say we have like A, B, B, C, D, E, F, G. So in order, actually, let's change this a little bit. Yeah, so let's change this to maybe like AAA or something. That's good. Okay, so in order for a substring to appear some number of times, like let's think about what it means if some length isn't achieved. So instead of figuring out like what's the longest substring, I went and focused on what's the longest length of a substring we can get, right? So longest length of a substring we can get. So in this case, let's just say we tried some random length, right? Like obviously the biggest one you can get is like 10, but let's just try some random length. Like if we try some random length, like call it 5, and we say like, can we get a substring of length 5 3 times? Is that a solvable problem, and how long would that take? So for something like that, you would basically just loop through and you just keep checking, like, do I have a consecutive character? Do I have a consecutive character? Do I have a consecutive character? So in this case, it's like yes, yes, yes. So I have a substring of length 3, but then I have to start over. Then I have to start over. Then I have to start over. Let's actually change this D to something else to make it a little bit easier to read. So let's make this like a G or something. So that's kind of like an easy problem, right? And I'll show you how to do this with a little bit, like if this wasn't 5, this was smaller. Essentially, you just go down and you just keep taking the character count. And if the character count is long enough, then you have something. And if it's not, then obviously you don't. So obviously for something length 5, we can't get it, right? So what does it mean that we can't get length 5? Can we get a length 6? Well, obviously not, because length 5 isn't possible. So if we just have a range of numbers, let's call it, or even 1 or something, but let's call it 1 to 10. If we try 5 and it fails, that means this whole range is no good. Similarly, if we try 5 and it works, then we know this whole range is good, right? So what does that look like to you? Should be pretty obvious that that's a binary search. So essentially my idea was you just binary search some given number, and because the constraints are, let's take a look, 5 times 10 to the 5th. So basically my idea was you just binary search like 1 to 5 times 10 to the 5th, get some solutions, and this would basically be an log n solution. And the log n of 10 to the 5th is like 20. So this would end up being like 20 times 5 times 10 to the 5th. Which would pass, right? Because that would be like roughly 10 to the 7th or so. Roughly. And actually, yeah, I think so. It would be 10 to the 6th times 10. Yeah, I think that would actually be exactly 10 to the 7th. So that should pass. And so when they ended up running, it was kind of close though. So it ended up like passing sometimes and not passing some other times. So let's actually walk through how this would work. Like, let's just do a little dry run of this. With like a smaller amount of letters just to make sure this is clear, because we're going to apply this to the other solution that I came up with. So let's say 5 fails, right? And we're just trying a range 1 to 10. So 5 fails. Okay, well, that's no good. So now our new range is 1 to 4, right? Because anything 5 or bigger is no good. So now our new range is 1 to 4. So let's just pick some middle number. Let's just pick like 2. So we're trying to get 3 substrings of length 2. So let's kind of walk through how this would look. So we would say like, okay, we have 1 character, we have 2 characters. Okay, now we have a substring of 2 characters. So, and we can just make a hash map to store this. So we can just say like, okay, let's make a hash map of A's. We're looking for exactly 2, right? So we have 1 string here. Now we take the next character and it's an A as well. So we know that's another string, right? We don't, and the nice thing is you don't even have to shorten this to be a length 2 substring. Like you might think like, okay, this is actually 3 characters. So you might have to like shorten this part, right? You might have to have like a left and a right pointer and keep shortening it to make your valid window. You could do that, but you don't really have to. For example, let's say we're looking for a length 1 substring. This is 1. Now, if the second letter is also the same, you don't actually have to shorten your substring because you know that your substring will be long enough, right? Like as long as you add characters, every character you add will give you another substring, right? So like basically, let's say we're looking for substrings of 1A, like this is 1, this is 1, this is 1, and that is indeed right. So 1, 2, 3. Same thing for, we can show this really quick. Let's say we have 4 A's, and we're looking for substrings of length 2. So this is 1. Then we add another character that will give us another 1, and we add another character that will give us another 1. We don't actually have to shorten the substring. Because if we can get a substring of length 3, we can obviously get a substring of length 2 that ends with that same character. Right? Like if this is 1 and this is 1, that means if this is long enough to be length 2, that means obviously there's a substring in here that's length 2. It'll just be this one. So you don't actually have to shorten the left side. So here you would just get like 3. So hopefully that makes sense. But if it's a little bit counterintuitive, what you could do that might make like more sense is just keep a valid window. So let's say you're looking for a substring of length 2. You'd say like, okay, this is 1. And then when I go here, I'm going to shrink my window to this. This is another 1, and so on, right? And then once you start here, you say like, okay, I have to shrink my window completely because we have a new character. So this is a B now. So I have 2 A's. And for a B, I have 1. Then I get to a C, which is a completely new character, so I have to completely resize my window to just C. Then I get to G, which is a completely new character, so I have to completely resize my window. Then I get to A again, which is a new character, so resize the window. Then I get to this A, and then we have another 2. So we have 3 A's, so we can return this is true. Right? And that's kind of the idea. You just binary search for some given window length, right? Some given number. And then if it's true, then you just mark that down as this is possible, and then you get rid of the left side. And if it's false, you say it's not possible, you get rid of the right side, and you essentially limit, you're essentially getting the biggest number possible that way. So every single binary search would take O of n, and you have log n of them. So that's fine. But there is a huge optimization you can make here. And the huge optimization is, and I noticed this after, like I said, I got a bunch of TLEs. It would like TLE sometimes, not TLE some other times. So let's say our string is something else. Let's say our string is literally just like, let's say it's like this. Pretend, I don't know how many this is. Let's say we call it 20 A's. So what we can do is we can get the longest sequence, right, of the same character in our string. And this is going to be a huge optimization because right now we are binary searching from every single number, right? Like let's say this string was like 10, or let's actually just use some, let's actually, instead of this, let's just have some random number. So let's say we had a string of length 10 to the 5th, and our longest consecutive sequence, which is pretty easy, right? You just go down the character. If it's the same, add 1. If it's not, repeat, store the longest, pretty straightforward. Let's say our longest one was like 10 cubed, right? We just have 10 cubed A's. So let's say our thing is like A times 10 cubed, and then everything else is whatever. So we can make a huge optimization here. And so I would definitely encourage you to think of this before I tell you. So what optimization can you make for your constraints, knowing that we have this many A's? Like, how can we narrow our left? How can we narrow our right? And so the optimization you can make is, if you have this, that means your right will never be bigger than this, right? Your right, like if the biggest possible subsequence you have is 10 cubed, how can our right, like we can't have a sequence bigger than that. So our right will just be this sequence. We can call this like result, right? So we can call this like, or longest or something. We'll call this result. So we have 10 cubed A's. We can get that down a lot. Now that's going to help a ton because let's say all of our characters are unique. Like we just have a string of well, actually, it's not. No, actually, it will help it a ton. Let's say we still do have 10 to the fifth characters, but we just have a repeating sequence of something like this, right? So we just have A B C D E, A B C D E, A B C D E, A B C D E. So our longest sequence here will be one character, which means the biggest right value we have to check for is 1. So that gets our n log n down to a linear time solution because our left will be 1, our right will be 1, and then like there's only one value we have to check. That's like a huge optimization. But there's kind of like a little bit less than a 1 for the left. So like I said, let's say we have 10 cubed A's. What does that mean? Well, let's actually have a little bit less A's to make it a little bit more obvious. So let's say we have 5 A's. So what do we know for sure our smallest sequence has to be? Like anything smaller than this, we never have to check. The smallest sequence we need to check is going to be length of this thing minus 2, because this will always be a sequence, right? This will always be a sequence, or like if you want to draw it with a shorter window, this will always be a sequence, this will always be a sequence, and this will always be a sequence, no matter what the length of this is, right? Like this can be 10 to the fifth A's. So the sequence ending with the A2 before the last one will always work. The sequence ending here will always work, right? Now, if you want to make it the valid length, you can obviously start here. But yeah, so this sequence will always work, right? And starting at the first character in whatever we have, ending here. Then starting at the second character, ending here will always work, assuming this is 3 or 3 or more, right? And this sequence will always work. So all of these sequence are length. So if this result is 5, our length at 5 minus 2. So if we get some huge value, now we got our length. Like let's say A is 10 cubed. Now all we have to do is check 10 cubed minus 2 up to 10 cubed, including 10 cubed. So we only have to check 3 numbers. So that's the huge optimization. So initially I did a binary search, and then I was like, well, we can just get the longest sequence, and then based on the longest sequence, there are only maximum 3 numbers you ever have to check. It's going to be the length of the whole thing, the length of the whole thing minus 1, and the length of the whole thing minus 2. Now, the reason that you have to check minus 1 and minus 2 is because what if you have something like this, right? 5 A's and like this, a B, and then 5 A's and a B, and then 5 A's. So it's still possible to have this like triple sequence of 5 A's, right? You can just have it in multiple locations, but you will never have a sequence bigger than 5, and you will never have a sequence less than 3. That's the answer, because there's already a sequence of 3 A's that occurs 3 times in this 5. And so that's a huge optimization. So basically our left and right range will only be 3 numbers max, so we don't really need a binary search. Now the funny thing is, when I did do a binary search, it actually ran faster because I think it checks like, instead of checking 3 numbers, it'll check like 1 but that's totally random. So, but essentially that's all we have to do. And let's say our longest sequence was less than 3 or 3 or something, right? Let's say our longest sequence was 2. So then what numbers are we going to have to check? Well, obviously a sequence of 1 will not always work, actually, right? So actually that's not true. 1 will not always work, because if we have something like this, our longest sequence will be 1 character, but there is no solution here, right? There is no number that appears 3 times. But if the longest one, like let's say we actually had this, then our left side will be, so this is 2. We don't want to do 2 minus 2 because it's still possible for there to be a sequence of 2, right? For example, if we had something like this would be a sequence of 2. So we can't just like throw it away. But basically our left side will be the maximum of 1 and whatever that sequence minus 2 is, right? So 2 minus 2, which will just give us 1. So our left side will be 1, and our right side will be 2. Once again, only a few numbers. And if the longest sequence is length 1, then it's still going to be the same thing. Your left side will just be length 1, and then the right side will be 1 as well. So you only have to check 1 number. Because if the longest sequence is length 1, that means there are no repeating letters, so the longest thing you can have is 1 letter appearing 3 times. And that's kind of the key to this problem, and I thought this was kind of cool that I found, and I also checked the solutions, and no one really had this. So, oh yeah, like, and like I said, the binary search will pass. Yeah, the binary search will pass some of the time. Like it got TLE some of the time, but this absolutely passes because this is basically an O-of-n solution, right? We only check three sequences, and to check a sequence takes O-of-n. So now we got it down to O-of-n, and then we're gonna have a hash map in our actual helper function that checks is a sequence of some characters length actually possible, right? So if we have this array, it's a sequence of like 5 characters possible that occurs 3 times. So for that, we'll just have a hash map of every single letter and its count, and then once we reach a sequence of some letter 3 times, then we will just return true, otherwise we'll return false. So let's take a look at the code. It's going to be pretty straightforward. So here it is. So we have this check function that basically goes through our string, and we pass in some number, and that's like the sequence length that we're looking for. And we are essentially just keeping track of like if our sequence is long enough, like we basically just have, like I said, a sliding window. You don't have to shrink it. You can shrink it if you want to, but you don't have to do it. So essentially every time you get a new character, you reset your sequence length. And every time your sequence length is greater than or equal to x, that means that you have a valid sequence. So we just increment the count in our dictionary. And once we have 3 of that sequence, that means that it's possible to get a sequence of length x 3 times. And then we can return true. And then this little function just, it's not really a function, but this code basically just gets the length of the longest character in the, right, the longest sequence that is only one character in the string. Also pretty straightforward. You just maintain a count of your character. Anytime you have a new character, you reset it, and you just maximize the result. So like I said, we don't need a binary search. Our left side is now the maximum of 1 and the length of our longest sequence minus 2. And our right side is just the length of the longest sequence. So we only ever have to check 3 sequence lengths. So this is O-of-n, right? So we just check all 3 of them, starting from the biggest one. So like, let's say our sequence lengths that we have are like 765. So we basically just check in reverse order. If we got something of 7, then we don't want to even use these because we want to have the biggest one possible. So we try 7, then we try 6, then we try 5. If all of them fail, we just return -1. And yeah. Obviously, so I guess you could optimize it a little further now that I'm thinking about it. Yeah, you could optimize it even further, but it's not really going to matter in the end. So let's say you did have 765. You know 5 will always succeed because 5 3 times occurs in 7. So you could optimize it there too, where you could say, like, let's actually try these 2. If these 2 both fail, then 5 has to be a success. So like if your left is greater, if your left is like greater than 1 or something, your left will always work if these 2 don't. But whatever. I mean, this is like this is a loop of 3 times, right? So it doesn't really matter. So you can just like check them as well. And yeah, that's pretty much it. So we can run it, and it's super inconsistent in runtime. So I can even show you in my submissions. So we have like a runtime, super inconsistent. Like it's 3,000 sometimes, it's like 1,200 sometimes, it's 900 sometimes. But the nice thing is with this, it will never TLE. So maybe let's try to run it until it gets better than 3,000. Or if not, I can just show you my submissions. Yeah, so let's just take a look. So if we take a look at submissions, here it is. So sometimes you get like 3,000, sometimes you get 2,000, sometimes you get 1,000. It's kind of all over the place. Let me actually, here it is. Yeah, so you get like 1,200, 3,000, whatever. And if I go down, I think the best I got was like 900. And I can show you really quick the TLE code, which had the binary search, right? So this would sometimes pass, sometimes not. So this was the, I basically didn't use this part, and I just did a normal binary search. So with a normal binary search, it would, I think it's more right here. Yeah, so it would like TLE, and this was like only binary search. And like I said, you saw this check function, but instead of doing this optimization to get only 3 locations, I would just binary search everything. So I just binary search from 1 to the end of the string, and that was significantly slower. So I think they show you runtime. Yeah, so here you can see it was like 6,000, like 9,000. It was like very slow. So this optimization is very big because we basically get it down from n log n to n. And the constraints on this problem are kind of bad. So you have to do, you can do the binary search, like I said, and it will pass sometimes. Or you could do this and it will always pass. So this is going to be time O of n, because essentially this check function takes O of n to check, like, is it possible to get 3 substrings of length s? And then also when we're getting the length of the current string, obviously that's O of n because we were looping through our entire string. And this part, like I said, is only checking 3 indices. So this is constant time. So for space, it's also going to be constant time because in our check function, we use a default dict of every single character. So while we're getting these like sequence length, this can only be lowercase English characters. So as always, if you've been watching my videos, you can only have 26 characters. So no matter how big your string is, even though it's like 5 to the 5th, your dictionary will only be 26 length. So this is O1. So yeah, hopefully this is helpful. I did think this was kind of a cool solution. And it was kind of funny, yeah, that I didn't need to take too much time to do it because I basically wrote the binary search for the first one of these, and then I just copy pasted and it passed sometimes, and then I was like, well, there's probably something better because usually when you have a solution that sometimes passes, sometimes fails, there's probably something better because like that would be. There are solutions that are kind of close, where like it will sometimes fail, sometimes pass, depending on your language, which the constraints are kind of bad. I guess this one is kind of like that, where people's solutions, like if I just pull up random solutions, they do run kind of long. So the constraints aren't great, but obviously, like I said, with this optimization, it's not even close. So, yeah, hopefully this was helpful. And if it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.